Okay, I'm gonna start then. My name is Kourosh, and I joined Scale about a month ago, working on RLlib. Before that, I was a PhD student at Berkeley, UC Berkeley, working on RL, in context of robotics and design optimization. So I'd be happy to essentially provide some guidelines to how we approach certain problems, aligned with what the questions that you guys have asked. Yeah. Federico, do you want to go next?
Yeah, so I am a master's student in machine learning at KTH in Stockholm, and I've been interested in reinforcement learning for the past 2 years. And in particular, in this last period, I've been interested in multi-agent reinforcement learning, and I am using RLlib.
Let me start. So hi everyone. Great to see you here. My name is Sven. I'm the team lead of the reinforcement learning team at Anyscale. My team, Kourosh is a part of it, and he's probably new. You haven't met him yet, maybe, but we're responsible for developing, maintaining RLlib, which you're all using. I think I know most of you, except for Federico. I think you're, and Sebastian also. I'm excited to hear what you guys are doing. And yeah, let's hear everyone else what you do with RLlib. Also, always super welcome to hear feedback from you, especially constructive feedback. That's like more on the what we should change and what's terrible about RLlib. We're always happy to hear that and to add that to our list of things to do, because that's how RLlib gets better over time. And yeah, this sounds like a really interesting problem, Federico. We have been thinking about this, especially Kourosh has been thinking about this for the last couple of weeks, like a lot. So this sounds like fun.
Yeah. Let's go around the entire room and then come back to the question.
Yeah. Sebastian?
Sure. Hey guys. So I'm a data science intern over at Altair, and I've been working with reinforcement learning since March. So my project pretty much involves implementing an agent to drive a sailboat in a simulator. And for that, we've been using SAC. So we have a pretty big continuous observation space. And then eventually as we're learning about the SAC agent and how to optimize and whatnot, we're adding more boat controls to it. So it's been challenging, but pretty fun journey. So yeah, we're excited to learn more about reinforcement learning.
Yeah, I'm the maintainer of Gym and Petting Zoo and a handful of other of the large RL environment libraries. Recently, I took over the mini-grid and mini-world libraries that a lot of people use. I'm here to follow up on the past discussions of Petting Zoo in RLlib and the breaking API changes that we've been doing in Gym.
Hi, I am the creator of the Neural MMO platform, a large-scale multi-agent simulator for training on decades of simulated experience. And I'm also here about the Petting Zoo integration today, though I might bother Sven about a couple Neural MMO things if there's time with integration on that.
Happy with that. Yeah, thanks.
I can get directly to my question, which is about multi-agents. And basically, I've been reading some literature and I've seen a lot of methods in which there is an information exchange between agents, which is learned. So the problem is we want each agent to be aware of the other agents in the environment. And a naive way of doing this would be to just handcrafting some features to pass to the agent that represent information about the other agents. But an interesting approach is that each agent generates what we could call a message. And this message is passed to the other agents. And this procedure is differentiable, and therefore the agent learns how to produce a message. Mm-hmm. And so more generally, my question is, how is it possible to do this in RLlib? And if yes, how? And a bit more specifically, I'm interested in a setting where each agent has a quite different observation space, which is different in size and meaning, and therefore the model that generates the message can't be shared across all the agents, but each agent needs to have its own model that produces a message for the other agents.
Yeah, just to summarize the question, I think the question is more about like how do we share information between agents and between like models within RLlib context. So this question is like about essentially has multiple facets, I guess, to it. When we think about like sharing information, it can be categorized in different ways. One is that in multi-agent context, the agents can, I mean, is it possible in RLlib to share raw observation space of different agents between each other, right? So for example, agent one, for computing its value function, it needs to know, it needs to condition its model on the observation of other agents. And that's actually possible, like, and it's very straightforward. And we have like a very good example of this called Centralized Critic in one of the example things, and I can share it to you. But like, I guess I want to clarify that this is just like a non-differentiable information sharing, where you just have to augment current agent's state with the other agent's observations and like maybe actions. And that's done through some hooks that we have already in the RLlib, in the multi-agent API for the RLlib. And I'm going to show you how that's actually done. And then we get back to the more, I guess, challenging case where you want to have like a differentiable information sharing between agents. So this is my workspace. So this is called like Critic, Centralized Critic. It's under RLlib's example, Centralized Critics. There are two versions of this. There are two ways of doing this. And Centralized Critic2 is, I guess, the one that we have provided like built-in APIs for. So basically, in your constructor of essentially your config files, when you specify these multi-agent things, policies, very like there's a policy map and there's a policy mapping function. We also accept this observation function, where you basically pass in a function which takes in as input, it takes all the agent observations, and then you can essentially augment each agent's observation with the other ones, and then pass it to their individual policies. The way that it works is that basically, for this to work, you have to essentially provide the output observation space that you would see after this function is applied. So, for example, here, we have two policies, and we have like a centralized critic observer, which essentially is augmenting these observations for each agent. And the way that it works is that you get these agent observations, and then you basically construct this new observation, which is just a nested dictionary of, okay, what is my own observation? What is my opponent's observation? What is my opponent action, right? And this gets passed to the policy. So you should assume that your policy will get this observation, and it's going to be the new observation space. And in order to kind of like inform your policy that this is going to be the observation space, when you kind of pass in the parameters to these constructors, you should provide the correct observation space, not the original observation space, but actually the augmented one, right? So here we basically construct this observation space as a dictionary of, a discrete 6 for own observation, a discrete 6 for opponent observation, and discrete 2 for, opponent's action. And this is kind of like, once you get to the forward pass of your model, whichever it is, like it can be a PPO model, anything, right? You will get this augmented observation instead of just an individual observation from your original space. So I'm going to make a pause here in case there's any questions here. And Federico, if this kind of answers part of your questions.
Yes. The part about sharing the observation, yes.
Yes. So
Yeah,
now,
sorry, I have a question actually. Sorry, I have a stupid question. The opponent action, like how do you, is this like the opponent's previous action?
so opponent, I guess in agent, this is just as a placeholder right now, but like opponent agent observation also includes, it's a sample batch of essentially what you get from the agent. So it includes not only like observation, but also like, I don't know, actions, advantages, I guess, even, right? So the post-process agent observation that you can essentially pass into the other agent as well.
Okay. So this, okay, yeah.
Yeah.
So this is more for the training. Sorry, I'm not super familiar with this example either. So this is more for the training, for preparing the train batch then.
It is also used for during inference, right? Like, so basically you don't have, the thing is that with this flow, you cannot have independent observation spaces for inference and training. Both of them should be coherent with each other. You can ignore, I mean, part of it, like for, during action prediction, you can just ignore observation space that you have, but you will get it anyways in there.
Makes sense. Okay.
Yeah.
Thanks. Yeah, sorry.
Mm-hmm. Now, here comes the challenging part, right? Sharing information between between agents that also need to share gradients, share essentially neural network architectures between each other. And that is something that is not currently like elegantly built into RLlib. And we are thinking about changing it down the line. And we have a couple of like design explorations that we're doing here to just make it consistent with what we've been doing in the past, and also enable users to do this kind of stuff. But like, I can cover, like for now, I can cover what I think the hard way to do it right now is in RLlib, and then what are its limitations and how we are actually moving forward with, like, I guess, changing that part. Basically, whenever we want to share like differentiable stuff between agents, we have already some examples in the, I guess, in the algorithm folder. It's like, this is more like referred to as, a centralized training, decentralized execution, where during training, you may want to also share like models, neural networks, and maybe like a mixture for Q functions that basically takes a collection of tensors from all the agents and performs some like update on them, like uses them in some way, and then you do some back propagation, right? That happens during training, but during execution, you essentially treat each agent as an independent entity and like run with it, right? So we have two examples. It's called MADDPG, multi-agent DDPG, and also what was the other one? QMIX. Yeah. So QMIX is basically this thing where you have n agents. They provide a Q function value at the output, and then you have a nonlinear mixture over their Q function values to basically get the the environment's Q function, the Q function over all the agents jointly together. So for these kind of algorithms, in a nutshell, what happens is that you essentially need to create some sort of wrapper around your multi-agent environment to treat it, to make it look like a single agent environment, and build your policies in a way that has information about like everything, right? All the neural network parameters. So the difference between this and the other one, the previous version that I said, is that you can use existing, for example, PPO model, PPO policy, just to like, create n agents of them, and then run independent local observation through each, and then don't share anything between them. So that's what we talked about, I guess, in the previous approach. But here, because you want to share these gradients, you have to kind of encapsulate all of these neural networks under the same model, the same policy. So you have access to all of these at the same time. And to kind of like, so you don't have any dictionary, like any policy map. You have a default policy that controls that entire unit. And then basically once your environment is kind of wrapped in a way that it looks like a single agent, then you can just like, okay, treat it as a single agent trainer. So you pass in like a number of agents, I think, into the model. Inside the model constructor, you create like a collection of models and also like a shared, shared component. And then like, it's basically PyTorch from then on, right? Like you get the observation, it's basically looks like a single agent observation, but it's like nested. So you can actually index through it very easily to get the corresponding, like each agent's corresponding observation, and then run it through the corresponding neural network. Any question about like the high level approach on this? And I can show you an example of how it's done.
No, I fully get. Okay, yeah. It's
Okay.
actually unexpected.
Yeah.
So one of the limitations is that RLib's QMIX algorithm and MADDPG, to my knowledge, are only capable of handling these homogeneous observation spaces for the single agent. So what you mentioned before, Federico, where you need different observation spaces for the individual agents, that's currently not covered by the QMIX. But you could, of course, construct your own algo that's similar to QMIX, or that uses this shared policy that Kourosh just described, and that does have different preprocessors or different.
Yeah.
Well, it does allow for different observation spaces. Yeah.
Yeah. So in this example, I have actually shown your use case where you have a heterogeneous observation, not just for actions, but for input observation, but also on actions. Maybe agent A is like 3-dimensional input, 2-dimensional output, and B is like 2-dimensional input, 3-dimensional output, right? And how do we do this? And they share like a media-like encoder, right? They have like input encoders that are different, agent-specific. They share some, I guess, let's say transformer architecture or anything, really, right? Several layers, and then they also have like independent output heads at the output, right? How do we do this here? So you're seeing my screen, right? Yeah. So just to give you an idea, this is just like a custom multi-agent class that I wrote. It doesn't do anything. It's just a placeholder. Just for illustration, you have like action space, observation space, which is just this dictionary of things. I mean, this can be like, I guess, heterogeneous here. And you also have like a heterogeneous observation space, right? And then I guess these are standard attributes that you have to set for like these two. For like multi-agent environment, it's documented as part of RLlib. But like it's very like this is an environment like very consistent with multi-agent RLlib documentation, right? So you basically take an action dictionary in your step function, and then you construct these multi-agent dictionaries, which is like a observation reward and like done flag, right? And now to kind of wrap this into a single agent looking environment, right? What we do is like we essentially augment basically you create this custom environment there, and then you basically have to augment this observation space and action space to look like a single agent one, right? So what happens here is that you go through, for example, each agent ID here, and then you basically what I did was construct this thing. So basically it looks like something like this. You have, essentially like, for example, for policy A, it's a dictionary, first of all, where keys are policy A and policy B. And then for A, it's going to be like agent, opposite space of A, and then neighbors, which is basically a dictionary where for the other agent, you have like a B keyword, right? And then what's my observation space, right? If you had a C agent, you could like extend there as well, right? And same thing for B, right? So this opposite space that comes out is essentially this nested structure. And then your action space is going to be just like the inherited version because it was like homogeneous at the time. Now, okay, so when you want to take a step in the environment, you basically have to take this action dictionary, construct a single, like the original action space that you would expect in a multi-agent environment, run it through the environment, and then augment your observations, right? To look like this space, right? So in a single observation here, you would see both A and B, right? Whereas in the previous version, you would have only seen like, A and B, like then the model would expect to see one agent at a time. Here you would get two of them at the same time, right? Now, any question about like how we wrap the environment in a single agent one?
No, crystal clear.
Okay, awesome. Now it comes to the model, right? So within this model, which is going to be a Torch model v2, which is basically the base model for all RLlib models right now, we're going to have to construct all of the neural networks that we would need inside this. So there's not going to be like any higher level executor, which will create like copies of these for each agent. You have to kind of like write them here yourself, right? So basically, I'm going to come back to these like configurations that I'm doing, but like you have like a dictionary of encoders, right? Where it's basically a mapping of keywords to like their neural network, which is right now is just a linear layer from the kind of like the agent's observation space to a latent dimension, right? So for A, it's going to be 3 to 128. For B, it's going to be 2 to 128, right? So this is going to be a dictionary of encoders. You have like a shared several layers, right? And then for trunk, you have again independent linear layers from 128 to 2 to 3, right? And then you construct this neural network, module for them, right? Now, the observation space that you get here is like a flattened multi-agent observation space. In order to kind of like go back to the original structure, you have to kind of call its original space, right? And then construct your neural network sizes and dimensions based on these like, parsed version of the original space. And that's how we do it here. So you basically, the observation space here is going to get flattened. So if you had like 3, 2, 2, 3, it's going to be like 10 dimensional, right, for each agent. And then you basically have to reconstruct back the original thing, right? So in a nested dictionary, and that's how you do it. Like we retrieve the original space, how it was, and then we use that to construct our neural networks, right? And now during forward pass, basically what you need to do is like loop through each agent, right? This happened usually before, like in the previous version, it happened outside of this model, but now it has to come inside, right? You loop through the agents, you encode each agent specifically with its own encoder, right? You get the agent states, you get the neighbor states the same way, right? You do some pooling, for example, mean pooling, average pooling. You concatenate both, and then you pass them through the shared encode, stuff, and then use the trunk to kind of construct this. And then you have your like list of agent actions, right? And for value function, you may do something similar. I just didn't do it here. Then what you pass out is just the agent actions and the updated state if this was like a recurrent neural network, right? And that's it. So when it comes to the configuration setup, you don't have any multi-agent stuff anymore. It's a single agent from the point of view of the RLlib. And then you pass in like a model dictionary, which kind of constructs your original model. So you have a custom model and maybe a config dictionary that passes like these new things that we define, like latent dimension and things like that. Yeah, so that's pretty much how you would do it today. It's a bit hacky because, you're masking the fact that this is a multi-agent thing, but just treating it as a single agent. And you have like, if you, it's not modular. So if I want to reuse PPO, I cannot do it. I have to go ahead and like create like a new Torch v2 model, which is different than like PPO. Now, what we're doing, I guess, moving forward is like, how do we consolidate these things? How do we essentially share these modules in a more general way so we can actually use existing code, for example, for PPO? And then all we need to do is like pass in these like shared modules in there, and then they should have like all access to the same thing when you're inside these like models. So
Kourosh, can I ask a question real quick? I think I missed it in your environment wrapper. How are you tracking the rewards of each of the individual agents?
Oh, so I didn't augment the reward here, but basically what you can do is like pass in a dictionary of rewards out, and they will show up in the sample agent as they are, right? Like basically, I think that's the case. Am I right, Sven? Or do you have any opinion on that? I haven't actually looked into that yet, but I think the structures that you preserve here are going to get passed to the sample. Sven, you're mute. Yeah.
Yeah, sorry. I'm trying to think. Yeah, I think you don't have to change anything because this is your reward dictionary already, because env is already a multi-agent env, a self-done env. Let's see.
I mean, I can put a breakpoint in the forward function.
Yeah, I mean, the whole problem is still a multi-agent one, right? So you still have a dictionary of agent keys. That's not the point. The point is that your model now handles these different nested things where you have agent A and then it has a neighboring, and that goes through agent A's encoder and stuff. But for the rewards, it shouldn't matter, right?
Yeah. So because this I ran this and it didn't give any errors, I think you still have like this reward is the same structure that is preserved, like that it has. It's a nested one. It will get transferred to a sample batch, and
to the loss, and then into the loss function.
In the loss function and things like that. Yeah.
Yeah, so your loss function will have to deal with this multi-agentness. So similar to how QMIX right now does it, and which is kind of like what does it do? Like a sum or something.
Yeah.
Thanks.
Mm-hmm. Cool. Yeah, this was like, I guess, one of the hardest questions that we've been asked during office hours. That's why it took like a bit of time. But yeah, hopefully it will be helpful for a lot of folks.
Yes, thank you very much. The explanation was very clear. Now I know what to do.
Yeah. We will probably like also attach these files to the discussion. I'll hand it off to Christian. He'll take care of it.
But maybe of course give like a quick overview of what will change or what we think should change, or how we can make this better and less complicated.
Yeah.
To do this.
Yeah. So the way that we are thinking about doing this is that so we're gonna have this like right now policy is the owner of everything, and under that you have a Torch model v2, but like Torch model v2 is not independently doing anything. So you cannot really take out this model v2 and then run it through the environment and do inference with it, right? You have to like load the entire policy to be able to run that, right? So that's number one thing we want to change. We want to essentially have a thin wrapper around all these neural networks, which is, I guess, self-contained, and it can be run through like during inference, right? And then what this policy will now be called like unit trainer, which is essentially not a policy anymore. Your policy is like that model, right? That gets run on the environment. And what this unit trainer does is that during train, like it does more stuff than just like running the sampling, right? It computes the loss function and things like that, right? And for these kind of problems where you want to share parameters, what you need to do is that in this like unit trainer, you would construct these like shared components outside of the model, right? Outside of the policy model, and then pass pointers or handles inside of these like models. so that these models will have access to the same object during training. And then when you pass, for example, like, I don't know, a tensor through that, the gradient, like, and then you backpropagate, the gradient gets accumulated on the same set of parameters instead of like copies of things, and then you have to like do some syncing between them. This design basically tells like, tries to isolate these shared models from whatever the policy is, but also contain them when you want to run them together during inference. So that's kind of the high level. It hasn't been polished yet, but I guess once the design, a very clean design document comes out, we can share it between folks to collect feedback. Yeah.
Sven, how hard would it be to just add a feature that allows you to mark a portion of the observation space, or say, one gym.spaces object of the observation spaces as differentiable, like assuming that it is filled in by the neural net?
So you mean like in the sample batch, right, that you get?
Well, what I was saying is, like, let's say that you have an action in your action space that is communicate, and that outputs a box, a vector, and then that vector, then the environment takes that, or an environment wrapper takes that, and that becomes part of the observation space. So then either any agent nearby, if you want it locally, or any agent globally that observes that agent can observe the communication from the last time step. And then you would not need to make any modifications whatsoever to the network side, because all that's happened is essentially you've marked an observation as differentiable, and it would be handled statefully the same way as an LSTM state is.
But the thing is, like, under the hood, these are running on different actors, which have essentially a copy of these things, right? They live on different processes during inference. And
isn't this the same as the LSTM state, though?
No, the LSTM state is not. The LSTM state that comes from the sample batch doesn't contain the graph anymore. It's just a snapshot of the output, of the last output. If you had, let's see, if you had a series of LSTM states, then you could run those through an LSTM, and then you could backprop through the entire sequence, right? Then you would have like a static backpropagation through time kind of thing. But
if you just treat it the same as the state, then, and you do maintain that series, I'm just wondering if there's a way to cheat this into the same mechanism you use for the LSTM, and not require really, for your own storage, to cheat that into the same mechanism of your trajectory processor, and then not even have to have any user-side modifications for at least a large fraction of communication applications.
But how does RLlib know which, where this? So let's say you have one component in your observation that comes from another model, because it already passed through some original observation from the environment through some preprocessor or some encoder.
It would be associated with the agent that it comes from. So if your observation space contains like agent 1, a bunch of stuff, and the communication from agent 1, comma agent 2, all the stuff for agent 2, comma the communication for agent 2, then it's associated with that specific agent. Basically, what I'm proposing here is a way to add, you'd have to be able to explicitly mark a section of the observation as corresponding to a specific agent. And then naturally that gives you the ability to know where the communication, which agent to link that communication vector to.
This will be possible, but it doesn't preserve the gradients, right? Like, because of the problem I said, right? Like, once they get into the sampling side, right, they live on a different process.
They live on a different process?
Yeah, that's why we convert them to NumPy, right? So we can transfer.
We don't preserve the graph right now.
I see. You don't preserve the graph for LSTMs either, though. You just maintain a sequence of everything, right?
Correct.
So that's what I was trying to see if there's a way to do that, given that all the agents come from the same environment.
We don't. That's why our LSTM models always require the state outputs to capture that. You just store that, but it's not. We don't keep the graph. We just keep all these state outs.
So you have this,
and then later
you have the state out of communication.
The states and the policy match in that case, right? And LSTM is designed to work that way. In this case, you'd have states from other agents' policies that the learner doesn't have access to when it's doing the gradient update.
Correct. Yeah.
So, yeah. I guess I was sort of thinking of it the flip side. So like from the perspective of the agent communicating, it needs the upstream gradient from the agent that has observed that communication.
We can probably do this during training when we want to like loop through agents one by one. You can augment the second agent's observation with the tensors that agent one has already computed or something like that. And then, I mean, but there should be like a very complicated protocol that needs to be figured out.
I see why that's complicated. I was just wondering because if that worked, then you wouldn't have to modify user-side code in order to do fancy communication, right?
Yeah, it's already an advanced usage, so I don't think
fair. Hey, I mean today's advanced usage is tomorrow's every case, right?
Yeah, that's true.
This is something I'm looking to add natively in my framework without differentiability, but differentiability would be awesome.
For whatever good it does, what Joseph said about today's advanced use cases tomorrow's standard, that's like profoundly true. When you ask RLlib's limitations, I think the biggest one is if you want to do, the next new thing, which, like if you're looking at like how you fix transformers, you can do instantly. Doing whatever the next new thing is in RLlib, because it's so interlocked and like things like CleanRL, is really hard, as I'm sure you're aware. And this means that people using it inherently can't use state-of-the-art things, which is often where the people who want to use distributed RL and the advanced tools will be the most.
The petting zoo discussion, maybe, because we have two folks here.
And Jim.
Yeah, go ahead. So I just have some. So we have Rohan now on our team interning for the next couple months, and
I've spoken with him.
He's currently finishing the W robust implementation, but once he's done with that, and he's always has the PRs and reviews, so it's not much left. He will go full time on Petting Zoo, making sure that our adapter works, that all the bugs are fixed that are currently in there, and then we start adding test cases finally to RLlib that use NeuroMMO.
Great.
That's the quick update on our end. So we're finally getting to do that.
And I've already sent him a list of how exactly to best do that as well.
Perfect. Thanks.
My neural MMO part.
Anything else from your guys' side on that particular topic that we should pay attention to and should do definitely? Or
so I do have a few more things. I was waiting for you to. So my thing with Petting Zoo is so we discussed last time. What we were trying to advocate for was that, if pretty much all the other major multi-agent RL, not pretty much, literally all the major multi-agent RL libraries except RLlib use Petting Zoo as their internal API, and most of the multi-agent environments use it now, then it would be beneficial to Petting Zoo and RLlib in the community and save development costs to switch from your custom multi-agent API to Petting Zoo because they're equivalent. And so that's the thing that we had previously discussed and that you guys said that you'd have wanted to look into at some point.
Yeah, I'm afraid we still don't have a definite answer on that. As a first step, and maybe we'll do that, but maybe we'll just keep making sure that our adapter works 100% with all the different Petting Zoo API use cases and corner cases. And then it would be just as if we supported Petting Zoo fully, right? It's similar to how we can claim that we fully support Gym API, even though under the hood, RLlib is not operating on the Gym API. It's using.
I didn't know that you weren't operating on the Gym API under the hood now. Okay.
We don't. So it's the same. On the outside it looks like you can give us a Gym environment and it perfectly works. We vectorize and do all this stuff. But under the hood, we don't use Gym anymore. We basically convert it automatically into what we call a base end. And then operate on that.
Okay.
The reason being several reasons. One is vectorization. The other one is multi-agent. The third one is asynchronousness. We need to be able to have external environments and allow the environment to poll us and as a RLlib as a service environment. So as a first step we acknowledge that we have bugs on the Petting Zoo side. Our example is not complete and we don't cover all the cases. And we want to fix that first to make you guys happy and to fully be able to claim, yes, you can give us a Petting Zoo env and it will work. Okay, will work. Right now we cannot make that claim, unfortunately, and that's too bad. And we're trying to fix that right now. And then we can still decide, say later, does it really make sense? Should we get rid of our internal multi-agent and API?
So
yeah, it's just nice because the test cover. I was just going to say the test coverage is so wide. Like the space of multi-agent environments that people are using. I mean, we're only scratching the surface, and already we're doing things that are far, far outside of the norm of most academic RL research. So, like getting that wrapper working so that you natively support it, I think that middle layer, it's very difficult to not have bugs there, right?
I mean, the middle layer should just handle the interfaces, right? And we can essentially, I don't think that the test is that should cover that scope is too complicated, like too broad, right? Because you can just, I guess, sweep all the possible interfaces and things like that. Like think about logically, okay, what are the edge cases of this communication that needs to happen, and then cover that interface interaction, right? Because under the hood, you're still running, I guess, petting soup, right?
Yeah, I mean, in a perfect world, right? The hope is that you're able to, any bugs that arise as a result of the API get upstreamed to petting zoo to be fixed. And like, there is not the question of whether this is a bug in the RLlib integration or in the petting zoo API.
Yeah.
So the other thing I was going to talk about was Gym and the Python 3.6 separately. So for Gym, I know that you guys have been complaining a bunch about there being breaking API changes in Gym. In the next week, roughly, we're going to release the last release of Gym that has any new breaking API changes. We're going to do some bug fix stuff, and some changes to environments, and we're going to release a change where all the breaking changes become like on by default and permanent. But like all the new stuff to the core API is going to be done, released in a off by default manner, at least in like a week.
Awesome. That'll be 25 or?
I think it'll be 0.25. Yeah.
Okay, got it. Okay, cool.
And then there's still going to be some, of course, environment changes going on, but that's easy to deal with. And then the wrappers, Gym's wrappers are going to essentially be redone in full. When that's going to happen isn't entirely known. And then at some point after there's like a sort of stable release, we're going to go and completely redo all the vector API stuff to have it natively do good vectorization with asynchronous support, with infpool, which lets you use all the CPU cores and like all the stuff you would want it to natively do for vectorization. We do that with a good API. Just we want to get the base API and everything else stable and all the environment stable before you do that for what are hopefully obvious reasons. Yeah. Then in terms of petting zoo stuff, what we've been doing is after the petting zoo, after breaking changes are made to Gym's API, we've just been making them into petting zoo. So there's gonna be another release again this week that'll have all the breaking changes from the last batch to Gym finally released and out to petting zoo and supersuit. And then we'll be making the breaking changes from this release to truncation and rendering to petting zoo in some point in the near future, or in the next few months, more likely. The other thing going on is that in the make function of Gym, when you take the first step in an environment, we apply the env checker to it now, because none of the environments for Gym followed the API, especially not with the changes. But even before, they still didn't, ever. And this way, hopefully, you'll have a much higher level of API compliance going on. Another thing of relevance too, I know you support ProcGen in Gym 3. We have a maintained fork of ProcGen that hopefully will be linked to on the official repo soon. They're calling just ProcGen 2, for lack of a better name. But just ProcGen, except it's going to have documentation upside. It's going to support the actual Gym API. It's going to have bug fixes. It's going to be available on PyPI, basic stuff like that. For whatever good that will do you. And the final thing I wanted to mention was talk about Python 3.6. So a while ago, so whenever you guys try to upgrade versions of Gym and petting zoo, as we drop 3.6, you guys complained a bunch because you had to maintain 3.6 due to whatever the reasons are. Now the problem, the reason we drop 3.6 is quite literally every single library Gym depends on doesn't support 3.6 anymore. And there's various typing stuff in that was started 3.7 that we've been using. And so there's been that. And, Python 3.6 isn't even getting security updates anymore. There's, Python 3.6, bugs and active exploitation right now. They're never going to be patched. You can Google this on the CVE lists. But apparently, guys still had to have 3.6. So we went in the last gym release, we went and we actually re-added 3.6 support temporarily just for RLlib. They're going to have it depending. It's looking like we aren't going to be able to do that for the most part. And the reason that we probably aren't going to be able to keep doing the 3.6 support is that JAX doesn't support 3.6, and we're having a bunch of core API integrations going on with JAX, so that environments can be harder accelerated and run on GPUs if we've seen that before. So I don't know how you want to handle this, but like Python 3.6 has been, not supported by the other major libraries for a very long time. It has active exploitations a while that are allowed to be fixed. And like, if we're going to continue doing with harder accelerated environments, like it's not up to us anymore to stop supporting 3.6.
Yeah, I think the reason why we're still sticking to 3.6 is it's like more like array upstream thing. Less.
Yeah, that's what I was told.
We have moved all our tests already to 3.7, so we don't even. I don't think we can test thoroughly on 3.6 anymore. The RLlib stuff, but Ray still officially supports 3.6, so that's an issue there. Okay.
Does RLlib have to? Even if base Ray does?
Yeah, because it's installed together, right? Yeah.
Pip install Ray of RLlib.
Make a disclaimer, and that's I can ask whether we could. I think it's policy that we should all be on the same.
That's unfortunate, just because there's a lot of development happening on all the open source stuff in RL right now, and it's just like 3.6 is just being treated as end of life dropped. Right. So
3.6 was end of life dropped a year ago.
Yeah.
Yeah, makes sense.
And I understand that industries and partners potentially have this requirement. Exactly. It takes a long time to get it out. I'm just wondering, if you take a look at that list, if there are people actually doing RL. Oh, jeez. If there are people actually doing RL on 3.6, or if it's just Ray on 3.6, right?
Mm-hmm.
Because if it's just Ray on 3.6, it makes it so much easier for everyone involved to just drop it from RLlib at the least.
I'll ask again.
Because we're rolling to work on this, but with the newest stuff with Jax, this isn't even up to us anymore.
Yeah, makes sense. Okay,
Yeah, it's at this point, supporting this stuff, even if you continue supporting 3.6, it's really going to be nominal, because you're going to be missing all the new features, right? Like Jordan says, it's not even up to us. So you're going to be having old style gym without all the new stuff that you actually want to use if you want to get stuff done.
Yeah, makes sense. I will try to closely align with the gym updates and the API.
That'd be great
to make sure that they flow.
Then let me just ask one more thing. So gym this is going to start being released soon, but over the next 2 to 6 months, because the estimating time is hard, all the environments in gym are going to be hardware accelerated by default. Now there's like they'll run on GPUs or TPUs or whatever by default.
Mm-hmm.
So my question for this and for this is, this is 100 to a few thousand times faster than environments normally are, right? So my question is that, for a lot of libraries, you have to do semi-custom code to have them actually, support this. You have to do semi-custom code to actually have the environments, to have the learning codes of, function with harder accelerated environments with the proper performance improvements. So I'm just going to say, does RLlib have this? And if not, is adding that on your roadmap?
It's on our roadmap to support environments producing data on the GPU, TPU, and then without moving it to somewhere else, directly use it for learning. That's our. It's actually very close. We're actually very close to doing that.
Cool.
We've done some initial exploration as to how much it will accelerate.
Do you guys have any other questions for me about Gym or Petting Zoo or anything else?
Nope,
Very
not
good.
right now, actually. Yeah, thanks for all the updates and information. That was great.
All right. Thank you guys so much, and I will see you later. Joseph, can you call me for like 2 minutes?
All
So
right.
we lost the 2 other people who had questions.
Yeah, it's okay. Yeah, Manny, anything else? Otherwise, we can just continue this discussion. Awesome. Thanks so much, Kourosh. This was great.
Yeah.
Thanks for
Does Manny have any questions or no?
Yeah, Manny, anything else? Or...
No, I don't have anything else. I just made some popcorn and was watching.
Yeah, great. Thanks for
Have a great day.
All right.
Okay.
Then thanks everyone for your time and hard work. I'll see you in 2 weeks.
Bye, guys.
Thanks.
Bye.
Bye.